Okay, now we are going to discuss solution of non-homogeneous solution of non-homogeneous linear systems with constant coefficients. Okay, previously we discussed how to solve a system of homogeneous linear systems by using by finding their complex, so by finding their eigenvalues and eigenvectors, and then there were different cases if the eigenvalues are real and distinct, real and repeated and complex. Now today we are going to discuss how to solve non-homogeneous linear systems, which can be written in this form. I hope you know it. So I put a bar here under this x vector and f vector because they are vectors and A is a matrix. So this is a non-homogeneous linear system. For example, if we have a system of this kind, maybe let me show you some example. Okay, this one. Solve the following system. Maybe x, you can say that this is dx by dt is equal to negative x plus 2y minus 8, and then dy by dt is equal to negative x plus y plus 3. So this is a non-homogeneous linear system. And this can be written as, if we assume that we can write it in this form, d by dt of xy is equal to negative 1, 2, negative 1, 1 times xy plus some negative 8 and 3. Here we can have some different functions as well of t as well. So we, for example, we can have 8t and 3 to the power maybe minus 2t. So still it is a non-homogeneous linear system. So you should remember that here you should have only the function of t. Okay, here and here as well. So you can have this thing a minus 8t and 3 to the power minus 2t. So this is non-homogeneous linear system. So if we assume that this vector is x vector, then we can write this thing as x dash is equal to a, where a is this matrix, times x vector plus this f of t vector, where f of t vector is this, which is a function which contains only the functions of t. Okay, and here we have a coefficient matrix which is which contains only the constants, and this is again the x vector. So this is how we can have a non-homogeneous linear system, and it is obviously linear as well. Okay, because here we have linear x and y are in linear form. So now today we are going to discuss how to solve these kind of systems. Previously, we assumed that there is no, this function is 0, okay, in homogeneous linear systems. There are two methods, in fact, which we can use to solve non-homogeneous linear system. Number one is method of undetermined coefficients. And the second is method of variation of parameters. Method of variation of parameters. Parameters. Okay. The first method, we have already discussed this method for the case of single non-homogeneous linear ODE. I hope you remember it. Method of undetermined coefficients. Fortunately, the method of undetermined coefficient also work for the case of non-homogeneous system of linear differential equation with constant coefficients. It works, but it is not as efficient as the method of variation of parameters. So the first method now, undetermined coefficients. Okay. I hope you remember how to solve a single non-homogeneous linear system. There were, again, let me remind you a little bit. If we have a differential equation, maybe second order, is equal to some constant. I hope that you know how to find the complementary challenge. In this case, the general solution of this non-homogeneous single ODE was what? The general solution was it has two parts. The general solution is what? The general solution might be y of x maybe. It has two parts, complementary solution plus a particular integral or a particular solution. Okay. The complementary solution was what? It is the solution of associated homogeneous ODE. Okay. We write the homogeneous means we put the right hand side is equal to 0, and we write the homogeneous part of that differential equation means y double dash minus 2y dash plus y equal to 0. So yc was basically the complementary solution of the associated homogeneous differential equation. Okay. Now, the particular solution was what? In order to find the particular solution, we used an educated guess. Okay. Motivated by the form of the right-hand side function. Okay. If the right-hand side function was a constant, we assumed that yp of x is some constant a. If the right-hand side is 2t, maybe it is a polynomial of degree 1, then yp, the particular solution was what? It is some polynomial of degree 1. And for the different cases, for in the case of exponential function, we assume different particular solution. In the case of cosine and sine, we assume different particular solution. This was basically the method of undetermined coefficient for solving single non-homogeneous differential equation, but it should be linear. Okay. We find basically, we write the auxiliary or characteristic equation of this and characteristic polynomial. And then we find the roots of that polynomial. The roots were real and distinct and real and repeated and complex. And then we write the complementary solution and then particular solution. There was a glitch in method as well. We discussed that if our assumed particular solution also has a term which appears in the complementary solution, we had to modify our assumption of particular solution. There was a glitch in that method. Now, the same things apply for the system of differential equations as well. Now, I wrote here first this system. Now, the complementary solution, sorry, the non-homogeneous system of linear differential equation, their general solution will also have two parts. Okay, the general solution of non-homogeneous system can be written in the form of vectors. Basically, now X vector is it should contain complementary solution and then particular solution or particular integral. The complementary solution is again is the solution of associated homogeneous linear system. Okay, this is called complementary solution. I hope you can find it because we have discussed it already. Now, what is the particular solution? XP. XP is again, we start with an educated guess. Okay, an educated guess motivated by the form of the right hand side function. Okay, if the right hand side function is the right hand side vector is a constant vector, then we assumed a particular solution in the form of a constant vector. Okay. Similar to this thing, previously जो हमने system लिखा था, for example, x dash is equal to -1, 2, -1, 1 times x plus f was -8 and 3. Okay, if this is the non-homogeneous linear system, I hope you can find the complementary solution. The particular solution is what? We assume it A, B to constants because the right hand side is a constant function. If this is the solution, then it must satisfy this system of differential equation. Okay, we insert this solution in this system and try to find the values of these unknown constants A, B. Okay, so in order to insert this here in this system, we need xp dash. Xp dash kya hoga? Xp dash should be constant because it is xp dash should be 0 because it has constant entries. How to take the derivative of this vector? You take the derivative of each entry separately. Okay, and similarly, how to integrate this vector? You have to integrate each entry separately. Remember this. Okay, so if we insert it here, we get 0, 0 equal to -1, 2, -1, 1 times x. Now x should be xp now. So we have a b here plus -8 and 3. Now you have two equations in two unknowns. Okay, you have two equations in two unknowns. You can solve them simultaneously and get the values of the constants. For example, what do we obtain here? 0, 0 is equal to what? You simplify this, -a plus 2b, -a plus 2b, and then -8, -a plus b, -a plus b plus 3. Okay, this thing. So you put this equation equal to 0 and put this equation is equal to 0. You get two equations, two system of non-homogeneous, a linear non-homogeneous system. Okay, linear equations. Now you get a system of non-homogeneous linear equations. Okay, we are going back to linear algebra. Okay, linear algebra में आपके पास -a plus 2b is equal to 8 and -a plus b is equal to -3. So what do we obtain here? A linear system of equations, non-homogeneous. We can solve it by using matrix inversion method. We can right? Augmented matrix, we can solve it by using several ways. I hope you know how to solve this non-homogeneous linear system of equations. क्यों जी सब कर लेंगे? Anyone? I hope you can do it. I leave this thing as an exercise. So after solving this system, we obtain the values of A and B. The value of A is, I think, 14, we obtain, and value of B is 11. So our particular solution will be what? 14, 11. Okay. Once we obtain a particular solution, we can write the general solution because we already have complementary solution. Now we have particular solution. So by adding these two things, we can write the general solution of this non-homogeneous system of differential equations. Okay. The solution is written in my notes. You can see them. See that solution in the notes. I shall upload them today. I hope you'll find them in the evening, maybe after the lecture. Okay, now the right hand side was a constant vector. Now, what if the right hand side is of different form? Maybe another example, example 2, I have given in my notes. The left hand side, so this one is also different. 6, 1, 4, 3, and then here we have 6t minus 10t plus 4. Okay. Now, this vector it contains entries which are polynomials of degree 1. Okay. Now, the form of the particular solution which you assume is what? It should be a polynomial of degree 1 in both entries. So you should write here a2t plus a1, b2t plus b1. At both entries, the assumed particular solution should be a polynomial of degree 1. Okay. Then you insert this particular solution in this system, and you try to find the values of these constants, a1 and a2, b1 and b2. Okay, we have now 4 constants. So xp dash is what? Xp dash is a2, t get derivative 1, a get derivative 0, b2, t get derivative 1, and b1 get derivative 0. So xp dash should be what? It is a2, b2 is equal to 6143 times, here you have xp, a2t plus a1, b2t plus b1, and then plus 6t negative 10t plus 4. Okay. Now, in this case, you have t as well. Okay. So you'll get 2 equations. You have to separate the t term and the constant term, and then you can compare the coefficients of polynomial of degree 1 in both entries on the right hand side. Okay. By comparing, you can have 4 equations. Okay, I hope you can do it. For example, let me write it. You can take this thing on the right hand side as well. So we can write 0, 0 is equal to what we obtain after simplifying. We obtain 6a2 plus b2 plus 6 times t plus 6a1 negative b1 minus a2. This is a constant term. And in here, 4a2 plus 3b2 minus 10 times t plus 4a1 plus 3b1 minus b2 plus 4. Okay. So you get, after simplifying it, you get this thing. Now you can compare, you can write the left-hand side as 0t plus 0, and then 0t plus 0. Okay. Now comparing these two sides, you can write this equal to 0, this equal to 0, and this coefficient t is equal to 0, and this thing is equal to 0. So you get 4 equations. In fact, you get a system of 4 linear equations, non-homogeneous. Then you can use matrix inversion method or echelon form, or reduced echelon form means Gaussian elimination method or Gauss-Jordan elimination method in order to find the values of these constants A1, A2, B1, B2. Okay, I hope you can do it. If you have any problem, you can discuss this thing in the next lecture. Any question? So, everyone got it?
Yes, sir.
G.
Just confirming that the complementary solution will find by like ignoring the constant and just using doing the eigenvalue problem for it, right?
I don't get it. Can you?
Oh, I'm saying like for the XC solution, the complementary solution, we're just confirming that we're going to ignore the, for example, 60 and minus 10t plus 4 term, and we're going to solve the eigenvalue problem for it, right?
Yes. In order to find XC, we are going to ignore this term. We'll write the corresponding homogeneous linear system, and then we'll find the complementary solution for that homogeneous linear system as by finding their eigenvalues, eigenvectors, and so on.
Okay.
Okay. After finding the complementary solution, we'll move towards the particular solution, and then we assume the particular solution. We start the particular solution by assuming a guess solution, or by an educated kind of guess motivated by the right-hand side or the form of this function. If this function is constant, we assume the particular solution in the form of constants. If this is a polynomial of degree 1, we will assume a polynomial of degree 1 here with the unknown constants. Now, what if we have different functions here? Maybe another example, if we have a kind of exponential function here. For example, in example 3, I have given these kind of functions, minus 2 e raised power minus t plus 1, and e raised power minus t minus 5t plus 7. Okay. Now, it is basically a combination of two functions. We have an exponential function and then plus a polynomial function. Okay. As I already told you that we assume the particular solution by looking at the form of the right-hand side function. Now, this is, in fact, the right-hand side vector f of t, and it is negative 2 e raised power minus t plus 1, e raised power minus 2, minus t 5t plus 7. Okay, we can split this function into two functions. We can write here maybe e raised power negative 2, 1, e raised power minus t, and plus 1, negative 5t plus 7. Okay. Now we have two different functions. Okay. F of t is this now. One part, the first part is this, and the second part is this. The first part is it contains the exponential function, and the second part contains the polynomial of degree 1. Okay. We take the polynomial of degree 1 here. Here we have polynomial of degree 0, but still we can consider it a polynomial of degree 1 as a whole. Now, in this case, what we assume here as a particular solution Here we have exponential, and here we have to assume some constants, a1, b1 times e raised by negative t plus, here we have polynomial of degree 1. We can say that this is a2 t plus a3, and then here b2 t plus b3. Okay. Either you assume this particular solution, insert it here in the system of differential equation, and try to find the values of constants a1, b1, a2, b2, a3, b3. Or you can use the principle of superposition here. I hope you remember we had discussed principle of superposition for the non-homogeneous linear systems. Okay. Or you can say that this is your first particular solution. You assume particular solution only for this. Sorry. You split this function in two functions. So here for this term, you ignore this term and you retain only this term in that system. And by assuming that this is your first xp, means this is your xp1 and this is your xp2. Okay. In order to find the xp1, you ignore this term and this term in the system, and you solve the system with this term. Okay, you'll get a1 and b1. Okay, and then in the second term, you ignore this one, you take this one. Okay, in the right hand side of this non-homogeneous linear system, you take this one and you ignore this one, and then you find the xp2, second particular solution, separately. You can solve them separately as well. And then by using principle of superposition, you can add the particular solutions of these two systems, and then you can obtain the particular solution of this complete linear non-homogeneous system. Means, what does it mean here? Let me explain you a little bit more. Means you split this given system into two systems. X dash is equal to 6, 1, 4, 3 times x plus minus 2, 1 e raised power minus t plus 1 negative 5 t plus 7. So this is your system original. You split it into two systems. X dash 6, 1, 4, 3 x plus minus 2, 1 e raised power minus t, and then another similar kind of system, 6, 1, 4, 3 times x plus 1 negative 5 t plus 7. Okay. Now you have two subsystems of the given general non-homogeneous linear system. Okay. You solve this one by assuming xp1 this one, and you solve this one by assuming xp2 this one. You solve them separately. And then you can have the general solution x, which is xc complementary and xp. Okay, where xp is what? Xp is the sum of xp1 plus xp2. Okay. So you can split this general system into two subsystems. You solve them separately, and then by using principle of superposition, you can write the sum of two xp's. You get the xp, and then you insert it here in order to get the general solution. Okay. I hope you can do it. There are several other examples I have given in my notes. You can practice from the book, from the exercise of the book as well. If you have any question, you can ask me. And for the case of glitch in this method, there was a glitch in the method of undetermined coefficients, which we had discussed for the case of single non-homogeneous linear differential equations. The same kind of glitch basically that occurs there, that might occur here in this case, and accordingly, you have to modify the particular solution, the form of a particular solution, in order to avoid or eliminate that kind of glitch in this method. Try to read these things from the book as well. If you face any kind of difficulty, I'll discuss it in the next lecture. See.
Discussed a method where you wanted a linearly independent solution. What you do is you take to the power of dx over dx, take the integral, and we would then y equals get a formula where you give the integral of e to the power of dx.
So that was basically, you know, to find the second solution if you get only one solution.
Kind of matrix, we diagonalize it.
Huh. Well, basically, method of reduction of order is your second solution. If the first solution is known, you try to find the second solution. You're talking about this thing. Okay. When there's a glitch in this method, we use that method, but we can directly yes, yes. And then you use that formula of method of reduction of order, which we have discussed in order to find, if the first solution is known, then in order to find the second solution, we use that method. Okay. Okay, try to read these things in more detail from the book. If you have any difficulty, we can obviously discuss these things in the next lecture as well. And in the next lecture, we shall also discuss method of variation of parameters for finding solution of non-homogeneous linear systems. This method, in fact, is a kind of lengthy method, because if you try to use this particular solution, you have to solve, in order to find these constants, you have to solve a linear system which has 6 unknown constants. Okay, and that is again a problem, because it takes a lot of time and it involves a lot of calculations. So we, in case of this kind of, or big right-hand sides here, in case of these kind of functions, we prefer to use method of variation of parameter. That is relatively easy to, in computation point of view, as compared to this method. We use method of variation of parameters. Okay? We'll discuss it in the next lecture. Okay, if you don't have any question, I'm going to stop it here. See you in the next lecture, hopefully, inshallah.